The universe holds secrets that defy everything we think we know. Among the deepest of these cosmic riddles are the theoretical objects called dark stars. These are not simply dead suns or black holes. They are ancient, invisible giants made of something fundamentally different, and they could completely rewrite the rules of physics as we know them. By the end of this journey, you will have explored 25 of the most incredible undiscovered dark stars ever conceived, each a key to a different cosmic mystery. What if the very first star to ever exist is still out there, hiding in plain darkness? Could our own galaxy harbor a silent, gravitational phantom right next to its central black hole? Which of these hidden giants would force us to rethink our place in the cosmos? The very first star to ever shine might not have been a star at all, at least not in any way we would recognize. This is the primordial behemoth, a dark star number 1. Picture the universe in its infancy, a swirling, formless sea of dark matter and the first wisps of hydrogen gas. In this ancient chaos, a colossal knot of pure dark matter began to collapse under its own immense gravity. It pulled in the ordinary hydrogen around it, but instead of igniting the nuclear fusion that powers our sun, something else happened. The dark matter at its core, interacting through forces we barely understand, began to annihilate itself, releasing a flood of heat. This heat prevented fusion, creating a vast, puffy, and shockingly cool object. We are talking about a sphere of gas and dark matter potentially millions of times more massive than our entire sun, yet its surface would be barely warm to the touch, glowing a faint, deep red if it glowed at all. This behemoth would not blaze in the darkness. It would be a gravitational anchor, a seed around which the first ordinary stars and eventually entire galaxies could coalesce. Finding one today would be like trying to spot a black hole against the blackness of space, but without the telltale disk of superheated material. It would reveal itself only by the silent, irresistible tug of its gravity, perhaps explaining why some of the oldest galaxies we see spin faster than they should, as if clutched by an invisible, ancient hand. Its discovery would not come from any light it emits, but from the way it bends the very fabric of space around it. A primordial behemoth of that staggering mass would act as a cosmic magnifying glass, a gravitational lens of unimaginable scale. When light from a distant galaxy travels through the universe and passes near this invisible giant, the star's gravity warps space-time, bending the light's path. From our vantage point, that faraway galaxy would appear distorted, perhaps stretched into a faint, luminous arc, or even duplicated into multiple mirage-like images around a central point of perfect darkness. This is the gravitational lens anomaly. Astronomers have seen this effect before, caused by massive galaxy clusters, but the signature of a lone dark star would be profoundly different. A galaxy cluster lens is messy, its gravity spread across millions of stars and vast clouds of hot gas. The distortion it creates is complex and smeared. The lensing from a solitary primordial behemoth, however, would be clean, sharp, and eerily symmetrical. It would create a near-perfect ring of warped light, an Einstein ring, encircling absolutely nothing we can see. The challenge is immense. How do you distinguish this perfect dark ring from the lensing effect of a supermassive black hole? A black hole of similar mass would also create a ring, but it would typically sit at the heart of a bright galaxy, surrounded by a swirling, superheated accretion disk that emits powerful X-rays. The dark star's ring would hang in isolated silence, a ghostly halo in the deep field with no energetic core to explain it. Spotting such an anomaly would require painstaking analysis of the most profound images from telescopes like the James Webb, searching for perfect circles of warped starlight that have no visible source. It would be a signature written in bent light, a whisper from the dawn of time proving that the first structures were not what we thought. That ghostly halo of bent light would be a monument to the universe's infancy. But what if some dark stars are not just ancient relics, but windows into the fundamental fabric of reality itself? Our second undiscovered dark star is born not from cosmology, but from the deepest puzzles of physics. This is the quantum foam singularity. To understand it, we must shrink our perspective down to the smallest scales imaginable. At the level of the Planck scale, a distance so tiny it is almost meaningless to describe, spacetime itself is theorized to be not smooth and continuous, but chaotic and frothing. It is a seething ocean of virtual particles popping in and out of existence, and microscopic wormholes and black holes forming and evaporating in an instant. This is the quantum foam, the turbulent base layer of all existence. Now, imagine a vast concentration of a unique form of dark matter, one whose particles interact with each other through forces tied directly to gravity at this quantum level. Instead of collapsing into a traditional star or a black hole, this dark matter could stabilize a region of this quantum foam, blowing it up to the size of an entire star system. The result would be a stable, star-sized bubble of roiling spacetime geometry. From the outside, it would appear as a shimmering, fractal-like boundary in the void. Light passing near it would not just bend, it would jitter and fracture, as if looking at a reflection in disturbed water. The surface would not be solid, but a probabilistic haze, a place where the very concepts of inside and outside break down. Within this foam, micro-black holes would constantly form and evaporate, and in doing so, they would emit faint, sporadic bursts of a special kind of radiation. This is analogous to Hawking radiation, the theoretical glow emitted by black holes as they lose mass, but here it would be a crackling static of quantum noise emanating from the entire structure. Detecting such a thing would be the ultimate prize for a theory of quantum gravity. It would be a laboratory the size of a star, built by the cosmos, showing us how spacetime truly behaves when gravity and quantum mechanics are forced to shake hands. Finding one would mean we have finally glimpsed the stitches holding the universe together. The quantum foam's chaotic shimmer exists at the very edge of our physical understanding. But to find a dark star, we might not need to look for such exotic disturbances. Sometimes the perfect hiding place is not in the void, but within the darkness we already accept. Drifting across the Milky Way are immense clouds of cold gas and dust so thick they blot out the starlight behind them. These are dark nebulae, like the famous coal sack near the Southern Cross or Barnard 68, a pitch-black blot in the constellation Ophiuchus. They are cosmic shadows, and we assume they are simply nurseries for future stars, places where gravity slowly pulls matter together. But what if within that inky blackness, gravity has already finished its work, and we are looking not at a cradle but at a tomb? Our third undiscovered dark star is the dark nebula's heart. Picture one of these clouds, a formless, freezing expanse. Its structure, however, is not random. Observations show some dark nebulae possess a startling density and a peculiar, almost spherical shape that is difficult to explain if they are just passive clouds. The gravitational anchor needed to sculpt and hold such a dense, cold cloud could be a dark star sitting silently at its very core. This would not be a star that heats its surroundings. Instead, its immense gravity would act like a deep well, relentlessly pulling in the surrounding gas and dust over millions of years, compressing it into the opaque shroud we see. It is a cold, hidden engine, forever feeding but never igniting. How could we ever detect such a perfectly hidden object? The star itself would be invisible, but its influence on its dark cloak might leave subtle fingerprints. Instruments measuring microwave emissions from the nebula could find an anomalous, faint glow. This would not be the warm radiation of star formation, but a signature of cold dust that has been gently, inexplicably heated. Furthermore, the motion of the dust particles within the cloud, tracked by radio telescopes, might reveal a slow, swirling vortex, a silent whirlpool centered on absolutely nothing we can see. Finding a dark star here would transform our view of these cosmic shadows. The coal sack would no longer be just a hole in the starfield. It would be a monument, a vast burial shroud draped over a gravitational phantom, hiding an ancient secret in the most obvious place of all. That cold, hidden heart within a nebula is a prisoner of its own making, bound by the dust it has consumed. But not all dark stars are content to remain hidden in place. Some are cosmic nomads cast out into the deepest, coldest wilderness imaginable. Drifting through the immense voids between galaxies is the rogue wanderer, a dark star number 4. This is a solitary giant, completely untethered from the gravitational embrace of any galaxy, sailing through an ocean of near-total emptiness. Its journey likely began in violence during the chaotic dance of two galaxies colliding. As immense spiral galaxies merge, their gravitational fields become a turbulent storm, capable of flinging stars out into intergalactic space at tremendous speeds. We have observed these hypervelocity stars, suns ejected on one-way trips into the void. But if a dark star existed in one of those galaxies, perhaps orbiting near the supermassive black hole at the center, the same cosmic slingshot could have hurled it out with even greater force. Unlike a normal star, its dark matter core would not have been dimmed by the ejection. It would have remained intact, a gravitational bullet fired into the abyss. Now it travels alone, a perfect and pristine laboratory. In the utter silence of intergalactic space, far from the light pollution of galaxies and the distorting gravity of star clusters, the properties of its dark matter heart could be studied in ideal isolation. There would be no competing signals, just the pure, unadulterated gravitational signature of the object itself. Yet even in this profound emptiness, it might not be entirely alone. Over its billions-year journey, its powerful gravity could have slowly swept up the wisps of primordial hydrogen that float in the intergalactic medium, gathering a tenuous, diffuse atmosphere around itself. This captured hydrogen, chilled to near absolute zero, might over eons begin to clump and coalesce under the dark star's dominant gravity. The result could be the most bizarre planetary system in existence, a family of frozen, dark worlds orbiting an invisible sun. These would not be planets like Earth or Jupiter, formed from the leftovers of stellar birth. They would be planets whose very existence, whose orbits and structure, are dictated almost entirely by the dark matter anchor at their center. A single telescope detection of such a system, perhaps by the slight dimming of a background quasar as its frozen planets pass by, would reveal an entirely new archetype of cosmic architecture, a ghostly solar system born from exile and isolation, forever wandering the lightless tracks between the islands of the universe. A silent partner can betray its presence through the smallest inconsistencies in a dance. Among the most reliable cosmic clocks are the Cepheid variable stars, pulsating giants whose rhythmic brightening and dimming is as precise as a heartbeat, directly tied to their intrinsic luminosity. This makes them invaluable for measuring cosmic distances, but what if one of these celestial metronomes had an invisible dance partner? This is the binary shadow, dark star number 5. In a distant binary system, a Cepheid variable pulses with its steady, predictable rhythm while orbiting a companion we cannot see. At first, astronomers would note the perfect timing of its pulses. But over years of observation, subtle anomalies would emerge. The pulses would arrive slightly early, then slightly late, in a pattern that repeats over a much longer cycle. This is the telltale sign of an orbital wobble. The visible star is not moving in a simple circle. It is being gently tugged back and forth by the gravity of its massive, unseen companion. By meticulously tracking these timing variations, scientists could map the invisible partner's orbit and calculate its mass. The result would be baffling. The mass would be substantial, perhaps many times that of our Sun, yet no light, no X-ray signature, no stellar wind would ever be detected from that point in space. It would be a gravitational shadow with the weight of a star. The detective work deepens. Astronomers would then study the visible star's spectrum, looking for the Doppler shift as it moves toward us and away from us in its orbit. This would confirm the wobble and give the orbital speed. Combining all this data would paint a precise portrait of the dark companion, its mass, its orbital distance, even its approximate shape, all inferred from the ghostly fingerprints it leaves on its luminous twin. The Cepheid becomes a probe, a tool to study something that emits no signal of its own. Finding such a system would be a masterclass in cosmic deduction, proving that sometimes the most profound discoveries are made not by what we see, but by the silent distortions in the things we can. Our own galactic center is a place of unimaginable violence and light, a maelstrom dominated by the supermassive black hole we call Sagittarius, a star. But in that chaos of swirling plasma and twisted magnetic fields, a perfect hiding place exists. A dark star could be orbiting just beyond the point of no return, its presence almost completely obscured by the black hole's overwhelming fury. This is the galactic center obscured. Imagine trying to hear a single, soft whisper in the middle of a roaring hurricane. That is the challenge of finding a dark star here. Its gravity would be lost in the titanic pull of Sagittarius, a star, and any faint, cool glow it might emit would be utterly drowned out by the brilliant, superheated gas of the accretion disk. It would be the ultimate cosmic camouflage, yet even the most perfect hidden object can betray itself through its interactions. A dark star of significant mass, locked in a close orbit around the black hole, would not be a passive spectator. As it plows through the outer fringes of the black hole's accretion disk, its gravity would churn the superheated gas like a spoon stirring thick soup. This disturbance could create localized, violent turbulence, pockets of gas compressed and heated to extreme temperatures. The result might be strange, short-lived flares of X-rays or gamma rays that erupt from specific points in the disk at regular intervals, timed perfectly with the dark star's unseen orbital period. Astronomers see frequent flares from our galactic center, but most are random and chaotic. A pattern of precise, repeating flares from a stable location just outside the event horizon would be a glaring anomaly, a rhythmic drumbeat in the chaos. Furthermore, the dance between the dark star and the black hole would be a relentless source of gravitational waves, the ripples in spacetime caused by massive accelerating objects. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detects these ripples from merging black holes and neutron stars. The signal from a dark star spiraling around Sagittarius, a star, would be different. A continuous, low hum buried under other cosmic noise, a persistent vibration in the fabric of space emanating from the very heart of our galaxy. Finding either clue, the patterned flare, or the unique gravitational hum, would be like discovering a ghost dancing with a monster, its presence revealed only by the disturbances it leaves in the storm. That ghost dancing with the black hole is a master of gravitational disguise. But some dark stars might not hide their energy, they might transform it into a beacon of pure destruction. The seventh undiscovered dark star is the dark matter annihilator. This concept hinges on one of the most compelling ideas in modern physics, that dark matter particles are their own antimatter counterparts. If this is true, when two dark matter particles collide with enough energy, they would annihilate each other in a flash, converting their entire mass into pure energy according to Einstein's famous equation. Now imagine a dark star with a core so incredibly dense with this type of dark matter that these collisions are not rare events, they are a constant, seething storm. The heart of this star would be a forge of annihilation, producing a torrent of the most energetic particles in the universe, gamma rays, neutrinos, and cosmic rays. The signature would be stark, a mysterious point source in the sky pumping out these high-energy signals with absolutely no visible star, nebula, or galaxy to explain them. It would be like finding a constantly flashing lighthouse in the middle of an empty ocean with no island beneath it. Our best hunter for such a signal is the Fermi Gamma Ray Space Telescope, specifically its Large Area Telescope, or Fermi LRT, which scans the entire sky for gamma rays. Scientists using Fermi data are actively searching for exactly these kinds of unexplained point sources. They sift through the maps, looking for pinpricks of persistent gamma radiation that cannot be linked to any known object like a pulsar or a distant quasar. So why have we not found one yet? The annihilator dark star could be missed for two reasons. First, its signal might be incredibly faint. If the annihilation rate is low, or if the star is very far away, the gamma ray flux reaching us could be so weak it drowns in the diffuse background glow of the universe. Second, and more intriguing, its emission might not be steady. The annihilation process could be chaotic, surging and fading based on the internal dynamics of the dark matter core. It might flare up for a century, then fall silent for a millennium. Our telescopes have only been watching for a cosmic blink of an eye. A dark star that flickers could easily hide its most brilliant moments in the vast gaps between our observations. Finding one would be the ultimate confirmation of dark matter's particle nature, a cosmic engine turning the invisible mass of the universe into a torrent of light we can finally see. That annihilation engine transforms the invisible into a violent beacon, but some structures in the cosmos are even more fundamental, threads woven into the universe's fabric at its birth. Our eighth dark star is the cosmic string anchor. To understand it, we must step back to the first fractions of a second after the Big Bang. As the newborn universe expanded and cooled, physicists theorized that immense cracks may have formed in the fabric of spacetime itself. These are cosmic strings not made of matter but of pure, concentrated energy, thinner than an atom yet stretching across the entire observable universe. They are theoretical defects like cracks in ice as it freezes, but on a cosmic scale, each possessing unimaginable density. A cosmic string would be so massive that a single inch of it could weigh more than Mount Everest. Now picture the chaotic early universe, a web of these ultra-dense strings forming and vibrating. Where two strings crossed or where a single string tangled into a knot, space-time would be profoundly warped. This intersection would act as a powerful gravitational trap, a snag in the cosmic net perfectly designed to catch dark matter. Over eons, dark matter particles would stream through the universe and accumulate at this defect, piling up into a colossal, dense knot anchored to the strings. The resulting dark star would not be a sphere. It would be shaped by its foundation, likely elongated or twisted, a strange, filament-like structure glowing faintly with the gravitational energy of its birth. Its most revealing signature would be in how it bends light. A normal spherical mass creates a symmetric gravitational lens like the Einstein ring, but a dark star anchored to a cosmic string would create a lensing effect unlike any other. The string itself, with its linear density, would act as a razor-sharp gravitational filament, slicing across the sky and creating a duplicate image of any galaxy behind it, a perfect twin separated by a thin, dark line. The dark star not at its intersection would then add a second, more complex distortion, warping those twin images in a specific, predictable way. Finding such a paired anomaly, a sharp line of duplicated light with a strange gravitational knot at one point, would be a monumental double discovery. It would confirm the existence of both a new class of dark object and the cosmic strings themselves, proving that the universe's earliest imperfections are still out there, hidden in plain sight with dark stars as their telltale signpost. The cosmic string's sharp line of warped light is a signature of the universe's infancy, yet some dark stars could distort something even more fundamental than light or space. They could warp time itself. Our ninth undiscovered dark star is the time dilation echo. This is a theoretical object so incredibly dense and composed of such exotic matter that its gravitational field does more than bend the path of light. It stretches the very fabric of time. Near its surface, time would pass at a rate dramatically slower than it does out here in the wider universe. This is not magic, it is a predicted effect of Einstein's general relativity, but taken to an extreme we have never witnessed. A black hole creates the ultimate time dilation at its event horizon, where time effectively stops, but that boundary is a one-way street from which no information returns. A dark star with this property might offer a gentler, more observable slope into the depths of gravitational time warping. To understand the echo, picture a future spacecraft on a mission to study this object. From our perspective on Earth, we watch the probe approach the dark star. As it nears the object's powerful gravitational influence, a strange thing happens. The probe's radio signals, which have been arriving with steady regularity, begin to slow down. Each successive signal takes longer and longer to reach us, not because the distance is increasing, but because time itself is flowing more slowly for the transmitter near the star. The signal's frequency would drop, deepening into a drawn-out drone, a phenomenon known as gravitational redshift. If the probe were to fire a laser pulse directly at the dark star's surface, the effect would be even stranger. The pulse of light would strike the surface, and if the star has any reflectivity at all, bounce back. But from our distant vantage point, that round trip would take far, far longer than simple distance and the speed of light could account for. We would receive a faint echo of our own signal minutes, hours, or even years after we expected it, as if the light pulse was stuck in slow motion during its close encounter with the star's distorted spacetime. This object would be a natural laboratory for the most extreme physics. It would allow us to test theories about how matter behaves under time dilation that we could never replicate on Earth or even near a black hole. We could study how quantum processes or even the decay of radioactive particles are affected when time is stretched to such a degree. The monumental challenge, of course, is detection. We cannot send a probe to a dark star we have not yet found. The clues must be gathered from across the light years. One possibility lies in a natural version of the laser echo. If this dark star exists in a binary system with a regular pulsing star like a neutron star, the regular flashes from the pulsar would pass close to the dark star on their way to us. Each flash would be delayed by a tiny but potentially measurable amount, creating a predictable pattern of lateness in the pulsar's otherwise perfect clockwork. Finding such a pattern would require exquisite timing over years of observation, searching for a consistent gravitational delay that has no other explanation. It would be a whisper from a place where time itself runs slow, a cosmic echo reminding us that the universe's most profound secrets are not just hidden in space, but woven into the very rhythm of reality. Time itself bends around the gravitational phantom, but our next dark star has found a home in a place where even the fabric of space is stretched to its limit. Vast tracts of the cosmos are not filled with glittering galaxies, but are instead immense, empty deserts known as cosmic voids. These are the true wildernesses of the universe, regions hundreds of millions of light years across that contain almost nothing. They are not completely empty. A handful of lonely galaxies might drift through them like isolated ships on a dark sea, but the density of matter here is a tiny fraction of the cosmic average. According to our best models, these voids should be uniformly sparse, their gravity so weak that the few galaxies within them drift slowly and predictably. Yet, what if something is hiding in that nothingness? Our 10th undiscovered dark star is the phantom in the void. Imagine mapping the motion of every single galaxy in one of these colossal empty spaces. You would expect them to be moving gently apart as the universe expands, or perhaps drifting slowly toward the nearest dense supercluster of galaxies at the void's edge. But astronomers using the most detailed surveys might find a small cluster of these isolated galaxies behaving strangely. Their movements are not uniform. They show a subtle, shared drift, as if they are all being tugged by an unseen current. This is the ghostly signature of a dark star, a massive, invisible anchor sitting in the heart of the void. Its immense gravity, though isolated, is enough to impose a faint order on the few galaxies nearby, pulling them into a slow, silent dance around a central point of perfect darkness. The painstaking work to find it is a triumph of cosmic cartography. Instruments like the Sloan Digital Sky Survey have mapped the positions and redshifts of millions of galaxies, allowing scientists to construct three-dimensional maps of the universe's large-scale structure. Within these maps, they can identify voids and then study the velocities of the galaxies inside them with extreme precision. The goal is to create a map of the void's total mass distribution, inferred from the motions of the visible matter. In a normal void, that distribution would be smooth and diffuse. The telltale sign of the phantom would be a sharp, concentrated spike of gravitational influence with no luminous source to account for it. It would be a massive knot of missing mass right in the center of the cosmic desert. This discovery would force a dramatic rethink of how voids form. Our standard models suggest they are simply the low-density flip side of the high-density filaments and clusters, regions that lost the cosmic lottery of initial density fluctuations. A dark star of such mass could not form in a void. It must have formed elsewhere in a much denser environment long ago. Its presence there means it was somehow ejected, a gravitational cannonball fired into the emptiness during an ancient, violent encounter, and now it sits alone, the undisputed monarch of an empty realm, its presence betrayed only by the silent sway it holds over the last lonely islands of light. A monarch ruling an empty void exerts its power through silent, irresistible gravity. But what if a dark star could announce its presence not with a tug but with a song? Our 11th undiscovered dark star is the resonant frequency emitter. This object challenges the very foundation of how we think dark matter works. Instead of interacting only through gravity or through the rare self-annihilation we discussed earlier, this dark star is built from particles that feel a hypothetical new force, a fifth fundamental force of nature unique to the dark sector. This force would cause its core to behave not like a static lump of matter, but like a dynamic, vibrating sphere. The entire dark star could thrum like a colossal bell, oscillating at specific, pure frequencies determined by its internal structure and composition. These vibrations, however, would be mostly locked away, invisible to us. The magic and the potential for detection happens at the boundary where this dark object meets the ordinary universe. Space is not a perfect vacuum. It is filled with a tenuous, ionized gas known as the interstellar plasma. This plasma is electrically charged and highly responsive to electromagnetic forces. As the dark star vibrates, the mysterious new force governing its particles could, in theory, couple weakly with this surrounding plasma. Think of it like a tuning fork placed near a thin membrane. The fork vibrates silently in the air, but when it touches the membrane begins to tremble, translating the vibration into sound we can hear. In this cosmic analogy, the dark star is the tuning fork, and the interstellar plasma is the membrane. The plasma would begin to oscillate in sync with the dark star's resonant frequency, and these oscillations would generate very low-frequency radio waves, a deep, persistent hum bleeding out into space. This is the signal we could potentially hear. Our most advanced radio telescopes, like the upcoming Square-Kilometre Array, are designed to be exquisitely sensitive to these kinds of low-frequency emissions. They will listen to the universe with a clarity we have never before achieved. The challenge is monumental, however. The cosmos is already filled with natural radio noise, from the afterglow of the Big Bang to the crackle of distant quasars and the gentle sigh of our own galaxy. Finding the specific, steady hum of a resonant frequency emitter is like trying to identify a single, constant musical note being played by a single violin in a symphony orchestra that is also experiencing a thunderstorm. Astronomers would need to filter out all known sources of interference, searching for a pure, unwavering tone that has no counterpart in our catalogues of celestial objects. They would look for a point source that emits nothing else, no light, no X-rays, just this persistent, low radio hum. If found, it would be a revolution. It would not just reveal a dark star, it would provide the first experimental evidence for a new force in the universe, a hidden interaction that has been shaping the cosmos in silence since the beginning. The dark sector would no longer be a monolithic mystery. It would have a rich, dynamic physics of its own, and we would have heard its first faint song. That resonant hum would be a whisper from a hidden force, but some dark stars might be hiding in the most crowded places imaginable. Orbiting our galaxy are ancient, glittering cities of stars known as globular clusters. These are spherical swarms containing hundreds of thousands, sometimes millions of stars, all bound together by gravity and dating back to the dawn of the Milky Way. For decades, astronomers assumed the dense knots of stars at the very hearts of these clusters were held together by the combined gravity of many stars, or perhaps by a medium-sized black hole. But there is another, more exotic possibility. Our 12th undiscovered dark star is the dark globular cluster core. Picture one of these ancient clusters, a shimmering sphere of ancient suns. As telescopes like Hubble and now the James Webb peer into their brilliant cores, they do more than take pretty pictures. They measure the precise motions of individual stars. By tracking how these stars move over years, astronomers can map the cluster's gravitational field, essentially weighing the invisible mass that holds everything together. The expected pattern is clear. The stars should orbit faster closer to the center, where the combined pull of all the central stars is strongest, creating a specific profile of velocities called a velocity dispersion. If a black hole sits at the center, the velocities of the innermost stars would spike dramatically, revealing the black hole's powerful, localized grip. A dark star, however, would paint a different picture. Its immense mass would be spread over a larger volume than a black hole of the same weight. It would be a diffuse, yet overwhelmingly powerful, gravitational anchor. The stars orbiting in the cluster's core would feel this dominant pull, but their velocity profile would be distinctive. Instead of a sharp spike in speeds right at the center, you would see a broader, smoother increase in stellar velocities across the entire inner region of the cluster. It would be as if the stars are dancing not around a pinpoint of infinite density, but around a vast, invisible sphere of influence. This subtle signature is what astronomers are now hunting for. Teams analyze the light from thousands of stars in a single cluster, using the Doppler shift to measure their speeds toward or away from us, building a three-dimensional map of motion. When they find a cluster where the core velocities are elevated in this specific, smoothed-out way, and where no X-ray source or other signature of a feeding black hole exists, the dark star hypothesis becomes compelling. It would explain why some of these ancient clusters seem too tightly bound, their stars moving just a bit too fast for the amount of visible mass we can count. A dark core could be the missing glue, a relic from the cluster's formation that has shaped the dance of 100,000 suns for over 10 billion years. Finding one would mean that the oldest structures in our galaxy are not just museums of ancient stars, but museums hiding a far older, darker secret at their very heart. A dark star could be hiding not in the void, but within a system we think we already understand. This is the exoplanet's hidden partner. Astronomers have now discovered thousands of planets orbiting distant stars, cataloging their sizes, orbits, and even their atmospheres. We map these alien solar systems with growing confidence, yet in some of these systems the data tells a strange, incomplete story. A star with several known exoplanets might show a subtle, persistent anomaly. The star itself exhibits a tiny, long-period wobble, a back-and-forth drift that cannot be explained by the combined pull of its known planets. or perhaps the orbits of the outermost planets are not quite as predicted, showing slight deviations as if they are being gently shepherded by an unseen hand. This is the classic signature of a hidden, massive companion in a wide, slow orbit. In our own solar system, this is the exact line of reasoning that drives the search for the hypothetical planet 9, a large body thought to orbit far beyond Neptune, its existence inferred from the clustered orbits of distant icy objects. Now scale that idea up dramatically. Imagine a star with its family of planets, and then, much farther out, a dark star completing a single orbit over thousands of years. Its gravitational influence would be faint but pervasive, a deep bass note underlying the higher-pitched harmonies of the inner planets. Detecting this partner is a test of patience and precision. It requires two primary methods often used in tandem. The first is the radial velocity technique, where astronomers use spectrographs to measure the star's light. As the star is tugged by an orbiting body, it moves slightly toward us and then away, causing its light to shift to bluer and then redder wavelengths. A dark star in a wide orbit would induce a very slow, very small version of this wobble, a signal that might only become clear after decades of meticulous observation. The second method is astrometry, the precise measurement of a star's position in the sky. A massive dark companion would cause the host star to trace a tiny elliptical path against the background of more distant stars over its long orbital period. Missions like the European Space Agency's Gaia spacecraft are performing this astrometry at an unprecedented scale, mapping the positions and motions of over 1 billion stars. By comparing Gaia's ultra-precise data over many years, scientists could one day spot a star that is not moving in a straight line, but dancing to the slow, silent rhythm of a dark partner. Finding such a system would be a profound revelation. It would mean that some of the exoplanetary systems we have so carefully charted are not complete. They have a silent, dark guardian in their outer reaches, a hidden architect whose gravity has quietly shaped the system's destiny since its birth. The silent guardian of an exoplanet system hides in the slow drift of its star's light. But some dark stars are not born in quiet orbits. They are forged in the universe's most violent explosions. When two neutron stars, the ultra-dense corpses of massive stars, spiral together and collide, they create a cataclysm known as a kilonova. This event blasts gold, platinum, and other heavy elements into space and typically ends in one of two ways: a slightly heavier neutron star, or, if the combined mass is too great, a black hole. But what if there is a third, hidden outcome? Our 14th undiscovered dark star is the post-collision remnant. Imagine that moment of impact: two city-sized spheres of pure neutronium, each weighing more than our Sun, slammed together at a fraction of the speed of light. In that unimaginable pressure cooker, the very neutrons themselves might not just merge, they might shatter. The extreme forces could break the neutrons down into their constituent quarks, creating a soup of exotic particles, including strange quarks. Normally, such a state of matter is unstable, but if dark matter particles were present or created in the collision, their unique interactions could act as a stabilizing force. Instead of collapsing into a black hole or exploding in a brilliant kilonova, the entire mass could settle into a new, stable form, a cold, ultra-dense ball of strange quark matter held together by dark matter's grip. This remnant would be darker than a neutron star and far colder, a dead cinder of transformed physics. Its formation would have sent a very specific shout across the cosmos, a burst of gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart Virgo have already detected the ripples from neutron star collisions. The signals match our models for merging neutron stars that produce kilonovas, but buried in their vast archive of data could be an anomaly, a signal that almost fits but not quite. The gravitational wave chirp from a collision forming a dark star remnant would have a distinct fingerprint, The in-spiral, as the two neutron stars spiral inward, would sound normal. But the moment of merger, the loudest part of the signal would be different. Instead of the sharp cutoff that suggests an immediate plunge into a black hole or the sustained rumble of a hypermassive neutron star, there might be a prolonged, dampened ring-down. It would be the sound of the new object vibrating and settling into its strange, stable form, its oscillations muffled by the exotic physics in its core. Finding this signal is a monumental task of cosmic forensics. Scientists must comb through the data, not just with the templates they have, but with new models that include the possibility of dark matter stabilization and strange quark matter. It is like listening to a recording of a symphony and trying to identify a single instrument that plays a note no one has ever written down before. If they succeed, the discovery would be twofold. First, it would confirm the existence of stable, strange quark matter, a theorized state that is denser than anything we know. Second, and more profoundly, it would provide direct evidence that dark matter plays an active, dynamic role in the most extreme events in the universe, not just as a passive gravitational anchor, but as a fundamental ingredient that can alter the fate of colliding stars. This dark star would be a tombstone for a cataclysm that chose a different path, a relic of physics pushed beyond any known limit. The cataclysm's remnant is a tomb of transformed physics, but some dark stars could be built from particles that rewrite the rules of magnetism itself. This brings us to dark star number 15, the magnetic monopole nexus. For over a century, our understanding of magnets has been absolute. Every magnet, from a simple refrigerator magnet to the entire Earth, has two poles, a north and a south. Cut a magnet in half and you do not get an isolated north or south, you get two smaller magnets, each with its own pair of poles. This duality is baked into our equations. Yet many physicists suspect this is not the full story. They theorize the existence of a magnetic monopole, a particle that is just a pure north or a pure south magnetic pole, a solitary point of magnetic charge. If they exist, they would be relics from the universe's first moments, created when the fundamental forces split apart. They are predicted to be incredibly massive and exceedingly rare. Now imagine a dark star that formed in a region of the early universe unusually rich in these particles. Over billions of years, its gravity could have swept them up, concentrating them in its core. The result would be an object with a staggering, permanent magnetic field generated not by swirling charged matter, as in a neutron star, but by the aligned poles of countless captive monopoles. This dark star would possess a magnetic field of almost incomprehensible strength, yet it would emit no visible light from its surface. It would be a dark magnet of cosmic scale. This immense, invisible field would not lie dormant. It would act as the most powerful particle accelerator in the galaxy. Charged particles like protons or atomic nuclei drifting through space would be captured by the field and whipped around at velocities approaching the speed of light. Gaining tremendous energy, these particles would eventually be flung out into the cosmos like cosmic bullets. These are what we call ultra-high energy cosmic rays, the most energetic particles ever detected. They carry more energy than a major league fastball, all compressed into a single subatomic particle. For decades, their origin has been one of astrophysics' greatest puzzles. When these rare particles strike our atmosphere, we can trace their paths backward. Yet, time and again, those paths lead not to brilliant quasars or active galaxies, but to seemingly empty patches of sky, voids with no known source powerful enough to create them. A magnetic monopole nexus would be the perfect solution. It is an engine of immense power that is completely dark. It could sit in one of those voids, its monstrous magnetic field silently manufacturing these extreme particles and firing them across the universe. Its detection would therefore come not from seeing it, but from solving a century-old mystery. By mapping the arrival directions of many ultra-high-energy cosmic rays and finding a statistically significant cluster pointing back to a specific dark region of space, astronomers would have a target. They could then train every available telescope on that spot, searching for any faint secondary signature, perhaps a whisper of gamma rays from particles interacting at the source, or a subtle distortion in the cosmic microwave background from the star's powerful field. Finding it would be a dual triumph, cracking the case of the cosmic rays and providing the first experimental evidence for magnetic monopoles, all hidden within the heart of a dark star. Our own galactic neighborhood holds a similar potential for hidden giants, not just in the Milky Way, but in the great spiral galaxy headed our way. The Andromeda Galaxy's vast halo, a diffuse sphere of ancient stars and dark matter stretching far beyond its bright disk, is the perfect hiding place for a dark star of immense scale. This object would not sit at the bustling center, but in the quiet outskirts, a gravitational phantom drifting through the sparse population of old stars and the invisible sea of dark matter that defines the halo's true mass. Its presence would be betrayed not by light, but by the delicate tracery of stellar streams, the cosmic breadcrumbs left behind by dwarf galaxies that Andromeda has consumed. As these small galaxies are torn apart by Andromeda's gravity, their stars are pulled into long, thin ribbons that orbit the larger galaxy like strings of pearls. These streams are exquisitely sensitive to gravitational disturbances. The gravity of a massive dark star passing through or near one of these streams would act like a stone dropped into a slow-moving river of stars. It would create a visible kink, a wiggle, or a localized gap in the otherwise smooth, arching flow. Astronomers can already map some of these streams, but the view is limited, like trying to trace a single thread in a tangled skein of wool from a great distance. This is where the next generation of observatories changes everything. The Nancy Grace Roman Space Telescope, with its extraordinarily wide field of view and sharp vision, is designed to conduct vast surveys of the sky. When it turns its gaze to Andromeda, it will not just take a portrait of the galaxy, it will census its entire halo. Roman will map the positions and motions of millions of individual stars in Andromeda's outskirts with stunning precision. This data will allow scientists to reconstruct the stellar streams in far greater detail than ever before, revealing their true, delicate structure. The hunt for the halo's secret will be a meticulous process of gravitational forensics. Scientists will create sophisticated models of how the streams should look based on Andromeda's known mass distribution. Then, they will compare those models to the exquisitely detailed map from Roman. Any persistent anomaly, a stream that bends where it should be straight or thins where it should be thick, would point directly to the location of a hidden perturber. By analyzing the shape and scale of the distortion, they could calculate the mass and orbit of the object causing it. Finding a dark star here would be a revelation on multiple fronts. It would prove that such objects can exist in relative isolation, far from the crowded galactic center. It would also provide a crucial clue about the nature of the halo's dark matter itself, suggesting that some of it is not smoothly distributed but clumped into these massive, singular entities. The silent dance of stars torn from ancient galaxies would finally point us to the invisible dancer hiding among them. The stellar streams in Andromeda's halo are a map of ancient collisions, but some connections in the cosmos might be far more profound than gravity. Our 17th dark star is the quantum entanglement network. This idea pushes into the most speculative realms of theoretical physics, a thought experiment that asks what quantum mechanics, the rules governing the very small, might look like when scaled up to the size of a star. At the heart of this concept is a phenomenon called quantum entanglement. When two particles become entangled, they share a single quantum state. Measuring the property of one particle, like its spin, instantly determines the property of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, a connection that seems to bypass the speed of light. Now, stretch that idea to a cosmic extreme. Imagine a dark star that formed in the universe's first moments, a time when everything was in close contact. Its core, made of exotic dark matter particles, could have become quantum entangled with the core of another dark star, or perhaps with an equally exotic object like a primordial black hole. These two massive objects would then share a quantum link across billions of light years. In theory, a significant event affecting one, like the absorption of a large cloud of gas or an internal phase transition, could cause an instantaneous, correlated change in the quantum state of its entangled partner. One star might subtly vibrate, or its internal pressure might shift. At the exact same moment, its twin experiences a change with no signal traveling between them. The cosmic implications are staggering. It would suggest that the universe at its largest scales retains a memory of its quantum origins, with invisible threads of instantaneous connection stitching together the cosmos in a hidden web. Detecting such a network is, for now, utterly beyond our reach. We struggle to maintain entanglement between a handful of atoms in a laboratory for more than a few seconds. The idea of detecting a change in a star-sized object caused by entanglement with another star is a monumental challenge. Any effect would be incredibly subtle, buried under the noise of gravitational waves, stellar activity, and the random churn of the universe. We lack even the theoretical framework to know what kind of instrument could measure a quantum state change in an object we cannot directly see. Yet, this dark star serves a crucial purpose. It forces us to confront the limits of our understanding and to ask fundamental questions. Does quantum mechanics, so successful in explaining the subatomic world, have any role to play in the architecture of galaxies and stars? Or is its influence washed out at large scales, leaving gravity as the sole architect? The quantum entanglement network is less a target for our telescopes and more a beacon for our imagination. It represents the outermost frontier of possibility, a reminder that the universe's deepest secrets may not just be hidden in darkness, but woven into a fabric of connection that defies our very conception of space and time. A planet with the breath of life orbits a star that cannot give it. This is the paradox of the biosignature anomaly, our 18th undiscovered dark star. Astronomers hunting for life scan distant worlds for chemical signs in their atmospheres, the most tantalizing being oxygen, especially when paired with methane. On Earth, these gases are overwhelmingly produced by living things. So, imagine the excitement of finding a rocky exoplanet with a thick oxygen-rich atmosphere, a world that looks, from a chemical perspective, alive. Then the confusion sets in. This promising world orbits a small, dim red dwarf star. Such stars are famously volatile, prone to violent flares that can strip atmospheres away, but that is not the core problem here. The deeper issue is energy. This type of star simply does not emit enough of the right kind of ultraviolet radiation to drive the photochemistry needed to build up such large quantities of oxygen abiotically through non-living processes. The numbers do not add up. The planet should not have this atmosphere, yet the data insists that it does. The solution may not lie with the star we see, but with one we cannot. A dark star could be the hidden key. Picture this system not as a single star with planets, but as a wide binary. The visible red dwarf is the secondary, smaller companion. The primary, dominating the system's gravity from a distance, is a dark star. This dark star does not blaze with fusion light, but its core is active with a slow, steady process, perhaps the decay of its constituent dark matter particles. This decay releases energy not as harsh ultraviolet, but as a gentle, pervasive bath of infrared radiation, a deep and constant warmth. This creates a second, invisible habitable zone, a bubble of clement temperatures centered on the dark star itself. The oxygen-rich planet orbits within this hidden bubble, warmed from the inside out by the dark star's infrared glow. while its official host star, the red dwarf, merely provides a point of light in its sky. This arrangement offers a stunning possibility. The planet is shielded from the sterilizing flares of its visible star by distance, while being gently incubated by the dark star's consistent energy. This could provide the stable, long-term conditions necessary for life not just to emerge, but to thrive and transform a planet's atmosphere. Detecting such a setup would require piecing together a gravitational and thermal puzzle. The planet's orbit around the red dwarf would show subtle anomalies, a wobble hinting at the dark star's pull. More tellingly, observations of the planet's thermal emission would reveal a mystery. The side of the planet facing the dark star would be warmer than expected, even when it is turned away from its visible sun. It would glow with an unexplained infrared heat, as if warmed by an invisible fireplace. Finding such a world would revolutionize astrobiology. It would mean that the search for life must expand into the shadows. The cradles of biology might not only orbit brilliant suns, but also gather in the gentle, unseen warmth of dark stars, places where life could flourish in a silence we are only beginning to listen for. The gentle warmth of a hidden sun offers one path for life, but the universe's first chapters were written in violence, not quiet incubation. Those ancient collisions left behind a permanent hum, a background noise woven into the fabric of space itself. This is the gravitational wave background, a low-frequency rumble detected not by telescopes that see light, but by using the cosmos' most precise timepieces. Networks of pulsars, the spinning neutron stars that flash with metronomic regularity, act as a galaxy-sized detector. By monitoring the arrival times of their pulses across decades, astronomers have found a common, faint drift, a signal that all these celestial clocks are being subtly sped up and slowed down in concert. The prevailing theory points to the combined din of countless supermassive black hole binaries merging throughout cosmic history. But there is another, more enigmatic chorus that could be contributing to this universal hum. A population of dark stars in the early universe, vibrating or spiraling together, could be a primary source of these space-time ripples. Their unique physics would compose a different song entirely. Unlike black holes, which are pure gravity wells defined by their event horizons, a dark star has internal structure. It could oscillate, its dense core sloshing or ringing like a bell after a collision. If these objects merged, the gravitational wave signal would carry the imprint of that structure. The merger's chirp would not end in the sharp, clean ring-down of a black hole collision. Instead, it might include prolonged frequencies, echoes, or a dampened finale as the exotic matter within the dark stars settled into a new, stable form. This distinct spectral fingerprint would be mixed into the background hum, a subtle contamination in the signal that challenges cosmologists to refine their models. To isolate it, scientists must become masters of cosmic audio engineering, filtering the expected black hole cacophony to listen for the residual tone that does not fit. Finding that tone would mean we are not just hearing the mergers of invisible giants, but listening to the unique vibration of dark matter itself, a fundamental particle signature amplified to a tremor that shakes the entire universe. The gravitational hum of ancient collisions is a whisper from the deep past, but a similar mystery might be unfolding right now in our own cosmic backyard. Beyond the orbit of Neptune, far past the icy realm of Pluto, lies a vast and mostly empty shell of frozen debris known as the Oort cloud. This is the solar system's final frontier, a reservoir of comets so distant that the sun is just a bright star in their sky. Here, in this profound chill, an unseen presence could be stirring the ice. Our 20th undiscovered dark star is not a cosmic giant, but a more intimate phantom, a planet-sized dark star hiding within the Oort cloud itself. This object would be cold, ancient, and nearly impossible to see, yet its gravitational influence could be written in the strange paths of the most distant objects we know. Astronomers call these extreme trans-Neptunian objects, or ETNOS. They are icy bodies with orbits that are highly elongated and tilted, taking them hundreds of astronomical units from the Sun. The peculiar thing is that the orbits of some of these objects seem clustered, as if something massive shepherded them into similar orientations. This is the core of the Planet X hypothesis, the idea that a large, unseen planet is lurking out there. But a traditional planet, even a super-Earth, might not have enough mass to create the observed effects, especially if it is on a wide orbit. A small dark star, however, with a core of dense dark matter could. With a mass several times that of Earth but compressed into an object perhaps no larger than our Moon, its gravitational pull would be deceptively strong and far-reaching. It would act as a silent shepherd, gently nudging the orbits of passing comets and icy bodies over millions of years, creating the very clusters that puzzle astronomers. Detecting this dark shepherd is a task of almost impossible difficulty. At such distances, it receives virtually no sunlight to reflect, and its own emission would be a faint whisper of residual heat, a fraction of a degree above absolute zero. Next-generation observatories like the Vera C. Rubin Observatory, with its immense mirror and ability to scan the entire sky every few nights, offer our best hope. It will find thousands of new distant objects mapping their orbits with unprecedented detail. The hunt for the dark star will be a statistical detective story. Scientists will build incredibly precise models of the outer solar system's gravitational landscape, including the known planets and the galactic tide. They will then see if the orbits of all the new ETNOS can be explained by these forces alone. If a persistent, unexplained warp remains in the data, a pattern of orbits that all point toward a specific region of the Oort cloud, that will be the target. Even then, confirming it is not a traditional ice giant will require more. The Rubin Observatory might glimpse it as a single, moving point of infinitesimal infrared light, a pixel that shifts position over years. Follow-up observations with the James Webb Space Telescope could then try to capture its spectrum, searching not for the signatures of methane or water ice, but for nothing, a featureless blackbody curve, the mark of an object with no atmosphere and no familiar chemistry, just cold, dark mass. Finding it would be a revelation that hits close to home. It would mean our solar system is not just a family of planets orbiting a star. It is a hybrid system harboring a relic from the galaxy's dark sector in its own attic, a permanent and hidden companion that has shaped the cometary cloud for eons. The implications would be profound, suggesting that such dark objects could be as common as planets, woven into the fabric of star systems across the Milky Way, forever unseen architects of the frozen frontiers. The silent shepherd of the Oort cloud is a relic of pure, cold mass. But what if a dark star could do more than just pull on things? What if it could transform the invisible into a faint but detectable light? This brings us to Dark Star 21, the action fountain. To understand this, we need a leading candidate for dark matter's true identity, a hypothetical particle called the action. The action was originally proposed to solve a deep puzzle in particle physics, but it also perfectly fits the bill for a dark matter particle. It would be incredibly light, billions of times lighter than an electron, and it would interact with ordinary matter only very, very weakly. This makes it ghostly and hard to detect, but it has one special property. In the presence of a strong magnetic field, an action can spontaneously convert into a photon, a particle of light. Now imagine a dark star built primarily from these actions. Its core would be a dense, churning sea of this exotic matter. Due to the extreme conditions and unique physics at its heart, this dark star would not just sit there, it would act as a factory. It would continuously produce new actions, which then stream away from its surface like an invisible solar wind. This is the fountain, a constant outflow of dark matter particles emanating from the star. These actions then fly out into the galaxy, traveling through the weak but vast magnetic fields that thread the space between stars. As they journey, a tiny fraction of them, encountering just the right magnetic conditions, would undergo that miraculous conversion. They would transform from an invisible action into a very low-energy photon, a radio wave. The result would be a faint, diffuse glow of radio emission centered on the location of the dark star. It would not be a bright point like a pulsar. It would be more like a hazy, radio frequency ghost, a soft halo of whisper-quiet static that other telescopes, looking in optical or X-ray light, would see as absolutely nothing. This presents a tantalizing opportunity for detection. For decades, scientists have been building incredibly sensitive experiments to hunt for actions here on Earth. The most famous is the Action Dark Matter Experiment, or a DMX. It uses a powerful superconducting magnet inside a cryogenic chamber, essentially a giant, ultra-cold radio receiver, waiting for the telltale signal of a galactic action converting into a microwave photon inside its magnetic field. The challenge is that they are searching for a diffuse sea of actions that supposedly fills the entire galaxy. The signal from that sea would be extraordinarily weak, like trying to hear a single instrument playing softly in a stadium full of people. A dark star acting as an action fountain changes the game entirely. Instead of listening for a faint whisper from everywhere, astronomers could point their detectors at a specific, suspicious point of radio haze. The fountain would provide a localized, concentrated source of actions, making the conversion signal potentially thousands of times stronger in that specific direction. It would be like that same instrument now playing a solo on an empty stage. Finding this radio phantom would be a 2-for-1 discovery of historic proportions. It would confirm the existence of a new class of dark object and, in one stroke, identify the elusive action as the true component of dark matter, solving two of the universe's greatest mysteries with one faint, ethereal glow. The action fountain's faint radio halo is a signal from a particle that might fill our universe. But could a dark star be composed of something that does not even belong to our universe at all? The 22nd dark star is a relic from a previous cosmos. This idea steps beyond the single Big Bang narrative into the realm of cyclical or multiverse cosmologies. Some theories suggest our universe is not the first and only one, but part of an endless cycle of expansion, collapse, and rebirth. Others, like certain string theory models, propose our universe is a three-dimensional brain floating in a higher dimensional space alongside other, separate brains, each with their own physics. In either scenario, when universes collide or a new one is born from the ashes of the old, it is possible that not everything is wiped clean. A stable knot of space-time or a clump of matter governed by entirely different laws could survive the transition. This dark star would be that fossil, a piece of a prior reality embedded in our own. Its properties would be fundamentally alien. To our instruments, it might appear as a region of space where the fundamental constants are subtly wrong. The speed of light in its immediate vicinity could be minutely different, or the strength of gravity could deviate from our universe's standard. More startlingly, it might violate conservation laws we consider absolute, like the conservation of energy or baryon number. Matter or energy might seem to appear or disappear in its presence, not through any process we understand, but because the very rules of existence are different for this object. It would be a cosmic artifact proving our universe is part of a much larger and much older story. Finding such a relic would require looking for the ultimate anomaly. Astronomers might detect a point in space where the afterglow of the Big Bang, the cosmic microwave background, shows a strange cold or hot spot with a sharp boundary, as if a window to another reality were imprinted on the sky. Or a gravitational wave observatory might pick up a continuous, unchanging hum with a frequency that does not match any known astrophysical source, a vibration from the relic's alien structure resonating through spacetime. Confirmation would come from impossibility. If every measurement of this object returned results that defied a unified explanation under our known physics, if it consistently broke the rules in ways no dark matter or black hole model could account for, then scientists would be forced to consider the extraordinary. This dark star would not just be a new object, it would be a message from beyond our cosmic horizon, tangible evidence that our universe is not alone, and that the story of everything has chapters written long before our own began. A relic universe's silent hum is a vibration from beyond our own laws, but the cosmos also crackles with sudden, brilliant shouts that vanish as quickly as they come. The sky is pierced by fast radio bursts, millisecond-long flashes of radio waves that carry more energy than our sun emits in 80 years. Their origins are one of modern astronomy's greatest puzzles, especially the rare ones that repeat, firing off multiple bursts from the same patch of sky. We have linked some to highly magnetized neutron stars called magnetars, but a problem remains. These cosmic powerhouses are born in the violent deaths of massive stars, surrounded by the expanding debris of a supernova remnant. Yet, some repeating bursts come from seemingly empty space, with no trace of a stellar explosion or a glowing nebula. This silence points to a different kind of engine. A dark star spinning with a ferocious magnetic field born from its exotic core could be the perfect culprit. We can call it a dark magnetar. Imagine an object with the intense magnetic field of a regular magnetar, but that field is not generated by spinning, super-dense ordinary matter. Instead, it is powered by the churning dynamics of the dark matter within it, a process that creates a stable, monstrous magnetic field without the need for a supernova's birth cry. This dark magnetar would spin silently in the void, its magnetic field lines twisting and storing immense energy like a colossal cosmic spring. When the stress becomes too great, the field lines snap and reconnect in a cataclysmic event, unleashing a focused beam of radio waves across the universe. From our vantage point, this appears as a fast radio burst. Because the object was not born in a traditional stellar explosion, there is no surrounding supernova remnant to see, no glowing cloud of gas to mark its location. It is a dark repeater firing its brilliant radio flashes from a point of perfect optical darkness. The hunt for these engines involves listening and then staring. Radio telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, constantly monitor the sky, catching the bursts and pinpointing their locations with incredible accuracy. Once the coordinates of a repeater are known, every other major observatory turns its gaze there. The Hubble Space Telescope, the James Webb, and powerful ground-based optical telescopes all look, searching for any hint of a host galaxy, a nebula, or a faint star. When they see nothing, when the most sensitive instruments in history find only empty blackness at the site of such a powerful explosion, the case for a dark magnetar grows strong. Its signature is the burst itself and the profound emptiness that follows. Each repeating flash is not just a mystery, it is a beacon from a completely new class of object, a dark star shouting into the radio silence, revealing its hidden, magnetized heart with a violence that leaves no visible scar. The dark magnetar's radio shout is a violent flare from a hidden engine, but the universe's most profound structures were not forged in such sudden bursts. They were set in stone during a quiet, fundamental transition in the first moments of everything. Our 24th dark star is a frozen relic of that instant, a symmetry-breaking artifact. To understand it, we must journey back to a time before stars, before atoms, before even protons existed. In the universe's first trillionth of a second, the forces of nature were unified. The electromagnetic force and the weak nuclear force which governs radioactive decay were one and the same, a single electroweak force. The cosmos was a seething, symmetric soup of massless particles moving at the speed of light. Then, as the universe expanded and cooled, it crossed a critical threshold. A field that permeates all of space, the Higgs field, shifted. This shift, called electroweak symmetry breaking, is what gave particles their mass. It is the moment the universe chose its rules, splitting the unified force into the two distinct forces we know today and allowing matter to clump and form. Normally, this transition happened uniformly everywhere, like water freezing into ice across an entire lake. But in some theoretical models, it did not happen smoothly. Bubbles of the new, broken symmetry phase could form and expand, colliding with each other. In the chaos, defects could have been trapped like flaws in a crystal. This dark star is one such defect. It is not a star of matter, but a frozen bubble of space where the Higgs field settled into a slightly different value than in the rest of the universe. This bubble would be a region where the laws of physics are subtly altered, where particles might have different masses or where certain interactions are enhanced or suppressed. On its own, such a bubble would likely have been unstable, collapsing or evaporating long ago. But if it formed around or captured a vast concentration of dark matter, that dark matter's gravity and unique interactions could have acted as a stabilizing cage, holding the defect intact for over 13 billion years. The result is a cosmic artifact of staggering importance. It is a direct physical sample of the universe in its first instance, a pocket of primordial physics preserved like an insect in amber. From the outside, it would appear as a perfect dark sphere. Its boundary would be razor-sharp, a wall where the properties of space itself change. This object would not glow with starlight, but it might emit a very specific signature. The altered physics inside could allow for the continuous production of exotic, massive particles that quickly decay into showers of known particles, like electrons, positrons, and neutrinos. This would create a faint but persistent halo of high-energy radiation around the object, a whisper of the extreme energies that filled the infant cosmos. Ironically, this is the very same realm of energy that scientists at particle colliders like the Large Hadron Collider are trying to recreate. They smash protons together at nearly the speed of light to briefly produce conditions similar to those just after the Big Bang, hoping to catch a glimpse of new physics or new particles. The symmetry-breaking artifact is doing that experiment naturally and on a cosmic scale. It is a permanent collider in the sky, running continuously since the dawn of time. Detecting it would require identifying a source that emits this specific cocktail of high-energy particles and radiation, but that otherwise absorbs all light, a dark sphere that devours photons but sings a song of ancient forces. Finding one would be more than discovering a new object. It would be like finding a living fossil of creation itself, a place where we could test by observation alone the theories about how our universe chose its fundamental shape. A sphere of perfect darkness could be the ultimate hiding place. This final dark star is not a natural phenomenon at all, but a cosmic fortress. It is the Dark Forest Sentinel, a megastructure built by a civilization that has chosen the ultimate form of camouflage. The idea stems from a chilling answer to the Fermi paradox, the question of why we see no evidence of other intelligent life. The dark forest hypothesis suggests the universe is a dangerous place, filled with civilizations that remain silent and hidden, fearful that any broadcast of their existence will attract predators or competitors. In such a universe, the most advanced species would not build glittering cities or send radio greetings. They would vanish. They would find a way to harvest energy without a trace, to become ghosts. This sentinel is that solution. Imagine a civilization that has mastered not only engineering but the physics of dark matter. They find a stable, massive dark star, a perfect source of immense gravitational and particle energy that emits no betraying light. Around this dark core, they construct a shell, a Dyson sphere, or a nested series of shells like a matryoshka brain, designed to capture every single joule of energy that the dark star produces. This is not a sphere to block a sun's light, but to contain something far more subtle. The entire purpose is to leave no signature, to become a hole in the universe's energy budget. The detection of such an object becomes a paradox. A perfect sentinel would be undetectable by definition, a complete absence, but perfection is hard to achieve. The first clue might be an anomaly of nothingness. In a detailed survey of a region of space, astronomers might find a patch that is unusually, profoundly blank. Across all wavelengths, from radio waves to gamma rays, there is simply no signal. No stars, no galaxies, no cosmic microwave background, not even the faint infrared glow of interstellar dust. It is a window of pure black, as if someone has cut a circle out of the universe. This itself would be a glaring signature, a shadow so complete it must be artificial. A more likely clue, however, is waste heat. Even the most efficient civilization cannot break the laws of thermodynamics. Using energy to compute, to live, to maintain their structure will inevitably produce waste heat. This heat must be radiated away, but a civilization hiding in a dark forest would not radiate it in a recognizable stellar pattern. They might emit it in a very narrow, artificial band of the infrared spectrum, or direct it all into a tightly focused beam aimed into the emptiness of intergalactic space, a cosmic exhaust pipe pointed at nothing. Our telescopes scanning the infrared sky might find a strange, pinpoint source that glows with a pure, single frequency of heat, with no accompanying visible object. Or we might see an object that is paradoxically cold, colder than its surroundings should allow, as if it is actively siphoning away thermal energy and disposing of it elsewhere. The sentinel represents the final, logical extreme of the dark star mystery. It takes us from natural wonders to existential dread. It asks us to consider that the most profound discoveries in the cosmos might not be ancient natural phenomena, but artifacts of intelligence so advanced they have chosen to become one with the darkness. Finding one would answer the Fermi paradox in the most unsettling way possible. We would know we are not alone, and we would understand why the universe seems so silent. The greatest structures may not be those that blaze with light, but those that have learned to master the dark, hiding in plain sight, forever watching and forever silent. From cosmic fortresses to frozen relics of creation, this journey through 25 undiscovered dark stars reveals a universe far stranger and more wondrous than we ever imagined. Each concept, from the primordial behemoth to the dark forest sentinel, is more than just a scientific hypothesis. It is a key that could unlock a different door in the mansion of reality, challenging the very foundations of physics and astronomy. These ideas push us to ask better questions, to look beyond the light, and to accept that the cosmos is built not just from what we see, but from what remains hidden in the silence. The search for these objects is not a passive wait for discovery. It is the engine of human curiosity, driving the creation of technologies like the James Webb Space Telescope, the Laser Interferometer Gravitational Wave Observatory, and the next generation of radio arrays. Each new instrument is built to listen more closely, to see more deeply, and to sense the faintest whispers of gravity from the dark. In chasing these phantoms, we are not just hunting for invisible stars. We are mapping the true architecture of the universe, learning the rules of reality from its most extreme and secretive architects. So we turn the question to you. After this voyage into the theoretical abyss, which dark star captured your imagination the most? Was it the action fountain with its faint radio glow, the biosignature anomaly offering a hidden cradle for life, or the terrifying possibility of the dark forest sentinel? Let us know your thoughts in the comments below. If you are fascinated by the deepest mysteries of space, be sure to subscribe. Our next deep dive is already waiting in the shadows.